Today, I want to talk about natural language processing. And one of the most basic things to start with is word2vec. Word2vec starts from an article in 2013 for vector representation for words by Mikolov. Very seminal paper. And so the goal is to convert a word to a vector so that your computer can understand the vector. So we use it in, for example, understanding the chatbots, any dialogue of your general intelligence, AGI, artificial general intelligence, but it can have applications beyond things like that. But it can have applications in, for example, in healthcare. For example, you have lots of reports for your clinical study, and you have millions, billions of records, and then you want to understand what happens to Alzheimer, and because each report refers to different patients, and a different patient has different characteristics, even different DNA sequence. And when the report talks about, for example, radiology, about this, all of these CT scans and all of these data, if you aggregate all of these data, you can see some patterns in, for example, about cancer or any other things in healthcare. And so it has huge applications. And but currently it is now being developed mostly in the United States of America, just because they have companies like Twitter, Facebook, and those things, and they need those engines. And so they need to develop some language models. For example, GPT-3 is the state-of-the-art that is developed by OpenAI, which is a company of Elon Musk. And they are working, for example, they use something like attention-based models, and they implement it with something like BERT or more advanced things like graph-based neural networks and graph embeddings in order to generate those low-dimensional representation. So they have a low-dimensional vector. But what is a language model? It's just a probability over for example, word 1 and word t. For example, in word ordering, for example, the probability that Aristotle is great should be greater than the probability that great Aristotle is. And so the most natural things that may come to your head is one hot representation. And it is, for example, you want to model cat as 0001. And so this could be 1 times 13 million. And so you see, it's a very long vector because this depends on the size of the vocabulary. It's high dimensional for any word. Just one of them is 1, the other one is 0. So this one hot representation does not work. So how can we reduce the dimensionality? Or we create an algorithm like word2vec to do this for us. So the goal is that we want words in different contexts to be far apart, and also we want to represent words such that it has semantic meaning. And close words should be close to each other. And the problem, you may say, okay, this is just dimensional reduction. And we know in dimension reduction that we can use SVD, you can use LLE, local linear embedding that I've talked in a lecture. But these algorithms, they do not scale. And the computational complexity of these are usually quadratic, so they cannot be applied to large datasets. But what is the solution? What is a fast solution? It could be word2vec. So word2vec is just one solution in 2013. Another solution is GLOVE in 2014. So as I said, when you want to represent X, for example, in SVD, it is use sigma V transpose. This is K by N, and this is your diagonal matrix. This is your D by K. D is the size of vocabulary, and the columns of U are eigenvectors of XX transpose. And columns of V, everybody knows those are eigenvectors of X transpose X. And when we say, for example, X is equal to U sigma V transpose, so this could be a low-dimensional representation, let's call it Y, and it can be referred to latent semantic indexing. So these things for example, starts from the concept of co-occurrence matrix. For example, you have a sentence like Mirza Khani, the only Fields medalist woman in the world, who is also Iranian, in the world that has got Fields medal. So Mirza Khani is the only Fields medalist. So you put Mirza Khani here, and then you create a matrix. Mirza Khani is the only Fields medalist. And here it is 1 because it comes after Mirza Khani. So they co-occur together. So you fill in this matrix, and this is your co-occurrence matrix. But GLOVE uses this explicitly. So what is the difference between the algorithm for GLOVE and word2vec in order to convert a word to a vector? And this is implicitly. So this is the difference. Of course, co-occurrence matrix that I said was first used for the pixels in an image, and then later people noticed that, okay, we can use it for NLP as well. And the reason that, for example, things like word2vec becomes very popular, because after training, you notice that, for example, if you subtract man from king and then add woman, it becomes queen. So this is vector, 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 and becomes another vector. So it has a kind of semantic meaning. So those cognitive scientists who want to talk about how can we understand, for example, analogy inside the human brain and those things may love this thing, because you've automatically from a raw text, just the text, you produce those semantic things, and no one is just supervise your learning. That's very interesting. But in the 2000 article that I said about word2vec, the author talked about continuous bag of words and also scriptgram. But when we say word2vec in general, for example, in your company, they usually mean the scriptgram implementation of that. They usually say that because it's much more convenient and efficient. But what is the difference between continuous bag of words and the default one, which is a scriptgram? for word2vec. In skipgram, you have a word, you have WT, and then you have some context around that word. For example, WT minus 2, WT minus 1, WT plus 1, and then WT plus 2. But the continuous bag of words is quite opposite. So we have some context, WT minus 1, WT plus 1, WT plus 2. It comes to the summit, and then you get WT after summation. So we want to, so in continuous bag of words, you have some context, and then you have some word. So from those contexts, you want to predict the word. You have context. So the architecture is like this. You want to have, it may remind you the encoder-decoder network. So it is a word, but here is a context. So context C and word W. So your input is just context, these context. And you want to predict the word. But in skipgram, it's quite opposite. So you have some words. So the architecture is quite opposite. You want to predict the context. And you have the input is given. Your word is given. So given the words, can you predict the context for us? And without loss of generality, in mathematics we write this, without loss of generality, we assume the context is just one word. So the continuous bag of word is like this. You want to predict the word. Just assume for simplicity that you use just one context. And you want to predict the word given the context. So you represent each word X as a one-hot vector, as I said, which is not good. So xi is 1 if I is equal to k, otherwise xi is equal to 0. And y represents the probability of the next word. So if you sum yi, then so each of them should be greater than 0 because y is a vector of probabilities. And h is a p-dimensional hidden representation. For example, when you say a big hedge fund, so this is a word, this is the context. So this is, for example, x equal to something. And so it's you represent it by a d-dimensional, your output has some probabilities. So let's say y, this is the output probability vector. So it is 0.01, and sometimes it is 0.09. So this may refer to 99. So this may refer to your hedge fund, and this may refer to big. So you predict, so you want to maximize the probability that all of these things happens. But I will explain it in details. And so you have this architecture. You have an output, you have word output, and you have some input. It is d-dimensional, and your W is d by p, and here W is p by d. So your hidden vector is p by 1, so it's just W transpose x, which is D by 1, and so this is P by D. So H will be the case column of W transpose if X is non-zero at this location. So this one. So you are just picking this column, because if you multiply with this 1, the location K, so you're just picking that at location K. So you have a probability, and you have this is your nonlinear activation function, which is acting on UI. And this is the phi is usually the softmax. For example, in word2vec, we use softmax. And this is the function is just e to the UI, and the denominator is a challenge. It's really a challenge because it is a summation over the corpus, and your corpus could be huge. So that's why things like negative sampling and hierarchical softmax comes into play, because the denominator is a challenge. How do you deal with that? In order to get rid of those problems, people invent. The author of that word2vec created two approaches. One of them is negative sampling, which converts that into a supervised learning, and the other one is the hierarchical softmax. So what I want to say is that phi of UI, for any UI, you have e to the v omega transpose VC over summation over W prime e to the v of omega transpose VC. And forget this is just the probability of word given the context. So the probability of word given the context is this. So this is just the inner product of your word and context. As a kind of measure, simple measure of similarity. You can use other measures as well, some kind of kernel, some cosines, and those things. But for simplicity of mathematical derivation, people notice that a simple inner product is enough for our purposes. So what is the cost that you want to maximize? What is the likelihood that you are? So statisticians like to maximize the likelihood, and machine learning engineers want to minimize the cost. So even economists want to maximize some benefit. So the cost is now the likelihood. We want to maximize the likelihood. Just like any other statistical problem, you want to maximize the likelihood. And your parameters theta, let's call it, it's just VC and VW. So board, context and word. And the probability of word given context is just e to the minus VW transpose VC divided by summation over the big corpus, which is a big problem. So I say again, this is a problem. This is a challenge. Even in any algorithm that you invent in graph neural networks, you have this problem with you. So in order to get rid of that, you may create some sampling techniques, anything. So there are hundreds of papers in order to resolve this problem. And you can invent your own approach in order to solve this problem. So what we want to do is to maximize this likelihood, which is now the product over words, because we want to maximize for all of the words. And we want to find theta, which is our parameter. As I said, theta is just words of context and vector of words. So if you write this, this becomes the product of e to the minus vc transpose v omega divided by summation over e minus vc transpose v omega. So if you